Today we're going to talk about more complex numbers. If you think back to our notes from yesterday, we first introduced this imaginary unit, this I, this thing that isn't a real number, but it's real because we use it as a placeholder, so it's important for us. And then we talked about, like, how can we simplify radicals with I? Like, if we have the square root of negative 81, then that's 9I. Okay, so we can use that I to help us. Then we did addition, subtraction, and multiplication. There's one operation I left off, right? Division. So that's what we have to look at today. How do we divide complex numbers? So this is Notes 3.2, Day 2, Complex Numbers. Our objective is simply that last operation of division. And we want to first talk about what it means to divide complex numbers. It doesn't really mean division, so that's the weird thing about dividing complex numbers. Okay. Dividing complex numbers basically means you're going to have two numbers in a plus bi form. The denominator then is going to have an I in it, but I'm telling you, you're not allowed to have I in the denominator. So our whole objective with dividing complex numbers is not really division. It's to get I out of the denominator. Now, how will we get I out of the denominator? We will multiply by something called the complex conjugate, which we're going to have a discussion about momentarily, so you know what a complex conjugate is. Again, the strangest part about division of complex numbers is that you don't really divide. In fact, all you do for division is multiply. So let's talk about complex conjugates. Conjugate sounds like a really complex word, but a complex conjugate is actually a really simple idea. So suppose we have a complex number in its standard form, a plus bi. To create its complex conjugate, we just take the operation in between the real and the imaginary parts, so the sign in between the a and the bi, and we change it. So the complex conjugate to a plus bi is a minus bi. These two numbers are complex conjugates, where a is the same value in both parts, b is the same number except for opposite signs. So I'm going to ask Cole to give us a complex number. He can make up any complex number he wants in a plus bi form. Just give me some number for the a and some number for the b so that we have both. Oh my goodness. 12 and 27. So we're going to say 12 plus 27i. There's Cole's complex number. He likes a challenge. Choose the big numbers. What's the complex conjugate to Cole's number? 12 minus 27i. Now, we are going to use complex numbers to do division. And we're going to multiply by the complex conjugate. So if we see 12 plus 27i in the denominator with a complex number, we're going to multiply by the complex conjugate, 12 minus 27i. So I'm going to go ahead and put those in their own groups of parentheses, and we are going to multiply Cole's complex number and the conjugate and see what happens. Something interesting might happen. Will happen. So this goes back to the question that Jacob answered at the beginning of class. Multiplying the numbers together, we're basically going to run through FOIL or distribution. So I'm going to take that 12 in the first parenthesis, and I'm going to distribute it to both terms in the second parenthesis. So 12 times 12, sounds easy for me, is 144. Okay. Then we're going to take 12 times negative 27i, and I get negative 324i for that. Big number. Use my calculator. That's okay. I'll tell you, most of yours will not be as big of numbers, so you won't probably need a calculator. But I like a challenge. Cool. Thank you. And then we're going to go back and we're going to pick up this plus 27i and we're going to distribute. So when I do positive 27 times 12, I'm going to get plus 324, and that's also going to have an I with it. And then my final multiplication is positive 27i times negative 27i. So I get negative 729i squared. Okay, remember that last term when you do the distribution is going to have the I squared term. What's interesting about that now that you look at your four terms? What's kind of cool that happens? Jackson? The I's in the middle cancel each other out. The I's in the middle cancel each other out. That was the math God's telling us. This is awesome. Life's too short. Okay, so negative 324i and plus 324i cancel out. And then I'm left with this 144 minus 729 times I squared. But what's I squared really? What's that?
Negative 1.
Negative 1. So I could say times negative 1. And then negative 729 times negative 1 becomes positive 729. And when I add those together, I get 873. Okay. So here lies the wonderful part about a complex conjugate. If you multiply any complex number by its complex conjugate, it will always come out to be a real number. The i's will always cancel each other out, and then you'll just have that I squared turn into negative 1, and you'll be able to combine two real numbers, and then you have a nice real number. So if we're thinking about the fact that in complex numbers division, we're not allowed to have i's in the denominator, how can we ever get rid of an I? Multiply by a complex conjugate. Okay. Now, we're going to do a little more practice with complex conjugates, but before we do that, I'm going to use the a plus bi and the a minus bi to show you a little proof that this will always come out to be a real number. And we can also use my little proof as a shortcut, so we don't have to do quite as much work every single time. Okay, so I'm going to start with the two complex conjugates, and I'm not going to use numbers this time. I'm going to use a plus bi and a minus bi. I'm just going to deal with these letters, and I'm going to do distribution and see what happens. So those numbers could be 12 and 27 like Cole picked. They could be any other number. Okay, we don't even know. So I'm going to start with the a. A times a is a squared. A times negative bi is negative abi. As a mathematician, I always like to write my letters in alphabetical order. Then I'm going to go to this second term, the positive bi. I'm going to multiply it by a. That'll be plus abi. Again, I can rearrange those because multiplication is commutative, and I like to write stuff in alphabetical order. Then I'll take bi times negative bi. Well, a positive b times a negative b is a negative b squared, and an I times an I is I squared, so I get minus b squared I squared. Interestingly enough, what happens to my middle terms? They will also cancel. So this is proving with a complex conjugate, my middle terms will always cancel. I will have a squared minus b squared times I squared, but I know that I squared is really -1. And so a squared minus b squared times -1 will always turn out to be a squared plus b squared. So that's going to be my shortcut that you're going to see me use in some future examples. If I'm multiplying by a complex conjugate, and I know that they're conjugates, they're the same numbers, just the sign in the middle is different, then I don't have to really do all the FOIL, because I know what's going to happen. I could just figure out what A and B are and square them. And they'll always be positives when I square them, because if it's a negative number, I'll square it and it'll end up being a positive number. So I'll just have the positives to add together. Let me take you back up to Cole's. Cole, was yours 12 plus 27? Okay, so 12 plus 27i. That looks like a 2, but that's a 27. And we're going to multiply it by a complex conjugate, 12 minus 27i. But I'm too lazy to do all my FOILing. So I'm going to cheat, and I'm just going to do a squared plus b squared. Okay? Where a is 12 and b is 27. So I would do 12 squared plus 27 squared. That's 144 plus 729. And that's 873. So I jumped right down to the last line of my work. Can I still do it the old way and FOIL and get my middle terms cancel out? Yes. But I don't want to, because I want it to go fast. So this is a shortcut that you can use. Now I'm going to do one extra example of the complex conjugate, then I'll show you one example of division, and then we'll get started on our homework for today. So I'm just going to make up another complex number. It could be any number. I'm going to choose some smaller values. So I'm going to say 4 minus 2i. What is the complex conjugate to 4 minus 2i? 4 plus 2i. This time, I'm going to do my shortcut first. I'm going to do my shortcut and see what real number it should equal, and then I'll show you through FOIL that it really is the same thing. So my shortcut says, figure out what A and B are. A is 4. B, you might say in the original, was a -2. So we're going to do A squared plus B squared. That'd be 4 squared plus. If you see that as a -2, then you're really squaring all of the -2. So you're taking -2 times -2, which would be a positive. So you don't have to include the negative there if you don't want to, but it's 16 plus 4, which is 20. So my shortcut tells me 20. We're going to verify over here through FOIL, and you may or may not write this down, that's up to you, that this is actually the case. 4 times 4 is 16. 4 times 2i is positive 8i. Negative 2i times 4 is negative 8i. And negative 2i plus 2i, or times positive 2i, is negative 4i squared. My middle terms cancel out. I have 16 minus 4 times -1. Which is 16 plus 4, which is 20. You can do it the long way, or you can agree to our shortcut, a squared plus b squared. It's up to you. That's what a lot of math is. Doing all the work to prove it works every time, and then using the shortcut from there on out. So I'm going to use the shortcut, if that's okay with you.
In the shortcut one, why did you do -2 instead of positive?
Well, only because, like, if I had originally said my complex number was 4 minus 2i, so, like, if you think about it in standard form, which would have been a plus bi, like, if that was my original standard form, then the real part was a positive 4, and the imaginary coefficient must have been a -2 because it says minus.
So if you put 4 plus 2i first, you use plus.
Yeah, and it's like, notice that it really isn't going to make any difference, right? So it's still going to be 16 plus 4. I'm just saying that because, like, it's really the negative, but if you just use the two numbers, 4 and 2, Skylar, you're always going to get the same answer that we get. And more people are probably likely to mess it up if they put the negative there, because then they might write -4. So if that's troublesome for you, know that you can always just take, like, the absolute value of the a and b and just use the positive, because we're always going to square it, so it's always going to be positive anyway. It doesn't really matter. It'd be the same if I gave you a complex number like -7 plus 3i. Well, a is -7, but when you square it, it's going to be 49. So it will be positive there. Okay, let's do one example of division, and then I'll have you get started on your assignment. So you got 1 plus 2i over 1 minus 3i. I kept the number small, so it'd be a little easy for us. Okay, so if you go back up to the top of the notes, the key piece about division is not that we're actually going to do any dividing. We're focused on looking at this as a fraction with a numerator and a denominator, and in the denominator I am not allowed to have I. So in the denominator I have 1 minus 3i. To get rid of I, if I'm working with 1 minus 3i, I can multiply by its complex conjugate. So I want to multiply that by 1 plus 3i. Now, if I multiply the denominator of my fraction by 1 plus 3i, then I must multiply the numerator of my fraction by 1 plus 3i. So you have to follow old fraction rules. Now, I'm going to work on my denominator first because that's the one that's the complex conjugate. So I've got my shortcut that I can use. So I'm going to focus on my denominator. Do you agree that 1 is a and b is, you could call it -3, or you could also just use 3? So I'm going to do a squared plus b squared. 1 squared plus, and then you decide if you're going to put in the -3 or if you'd rather just put in the +3. It won't matter because they'll both turn out to be +9. So I'm going to keep going. That's 1 plus 9, which is going to give me a denominator of 10. Are we okay with that? Okay. So have I done the thing that I said we should do? Get rid of I in the denominator? Yeah. So we're feeling pretty good. The rest of the work is multiplication, which we did yesterday. We will have to FOIL out the top and combine like terms and change I squares to -I because the top is no longer a complex conjugate. So I do have to run through distribution. 1 times 1 is 1. 1 times 3i is 3i. 2i times 1 is 2i. And 2i times 3i is plus 6i squared. Combine like terms. 3i plus 2i is 5i. And this will really be 6 times negative 1, so that will be a minus 6 at the end. And then I've got 2 real parts now. 1 minus 6 will be negative 5. And I have negative 5 plus 5i. If you have trouble like doing it all as a fraction and having a numerator and denominator, you could write those 2 parts out separately. Figure out your numerator, figure out your denominator, and then put them back together. Notice all 3 of these numbers share a common factor, so I can reduce each of them by a factor of 5. So this will be negative 1 plus I divided by 2. If this was like negative 5 plus 3i divided by 10, I wouldn't reduce if they all couldn't reduce. So you only reduce it if everybody can reduce. So division is really just a game of multiplication, and it's really multiplication twice. You do it in the denominator with the conjugates, and then you got to do it up in the numerator and actually FOIL or distribute things out.